Bismillah ar-Rahman ar-Rahim. We'll continue our discussion regarding TCP congestion control. We talked about the fact that the approach that's used by TCP is to try to detect the collision end-to-end without having full visibility to the network. And that's hard, as we know, because if there is any packet drop, we have to make assumption that this packet drop happened because of congestion. But we're not quite sure that this is really because of congestion, right? Because we don't have visibility to the network. So that actually forces TCP to make certain assumptions. For example, if the packet is dropped due to 3 duplicate acts, is this really serious or due to timeout? Which one is more serious? And what is the approach of TCP as a result of each of these events? So, so what TCP does is that it tries to use the approach that we explained last time, additive increase, multiplicative decrease. And what this means is it starts from a low congestion window, and then it increases linearly, and then if there is any event, then it drops. And the assumption here is that you can easily create congestion, but it's not as easy to clear from that congestion. So you probably can cause traffic jam in the highway, but you have to wait for a longer time until this traffic jam really clears. So that's why you have to drop, in many cases, drastically. You have to have drastic drop in the congestion window. And this is what we call a additive increase, multiplicative decrease. So with that, we were able last time to calculate the rough rate for the source. So when the source tries to send using a specific congestion window is the number of bytes that the source can send without having to wait for an acknowledgement to come. So this congestion window in bytes, if we divide it by the round trip time, it gives us rough estimate of the rate, the effective rate for the source at this point of time. However, this might actually go up and down depending on this variable congestion window. And we said that normally this congestion window is actually the minimum of 2 things. The congestion window at time t plus 1 is the minimum of 2 things. One is it's called a receiver window size. This receiver window size is the one that gets received in the acknowledgement. So every acknowledgement would have the receiver window size, which is the limit in the empty buffer for the receiver. So I cannot go beyond that by any means. And this is for flow control. Okay? So to avoid overwhelming the receiver, we need to abide by this receiver window. And the other component is the window at time t minus 1 plus 1. So if we increase the window size by 1, we said that for every acknowledgement, we increase the congestion window by 1. Okay? So if we start to increase by 1 and then we go beyond the limit of receiver window, then we stop. Otherwise, we keep increasing. Okay? So this way, this is for congestion control and this is for flow control. So this way I can abide by both. So I avoid overwhelming the receiver and I avoid overwhelming the network. Okay? So by this simple algorithm, we can avoid both. So the loss event happens because of 2 sub-events that might happen. Although a duplicate acts, we have to have 3 duplicate acts, or we have timeout. So which one is more serious, you think? The timeout is more serious. And to appreciate this visually, let's try to see a visual figure that will help us hopefully to appreciate each of these scenarios. So if I have a source and I have a destination, okay, so when I send the first segment 0, for example, I can send segment 1, I can send segment 2, I can send segment 3, assuming I have available size in the congestion window, right? So hopefully the destination will send me an acknowledgement. Here the acknowledgement will have acknowledgement sequence of 1, صح? Right? Assuming that segment 0 arrived, okay? So if we assume that segment 2 did not arrive, okay, and says segment 1, sorry, did not arrive, and segment 2 arrived, okay, what would be the acknowledgement sequence number here? Huh? Okay, yeah, 1, right. So this is the first duplicate act. So if segment 3 arrives, then I would send a 1 صح 1 صح ماشي ما انا محتاج عايز الناس ماشي 4 1 as well. So these are 3 duplicate acts. Okay. So assuming that the sender receives all these duplicate acts, it will go into a fast retransmission, as we explained before, right? So that indicates that segment 1 might have been lost or delayed, but is this really an indication that there is serious congestion in the network? Probably no. Why? Because there are some segments going through, right? So because there are some segments going through, that tells me that there is one packet drop, but that might be an intermittent event, right? But since I'm receiving duplicate acts, that indicates that other packets are getting through. صح كده? Whereas the timeout happens when, if I don't receive these duplicate acts, which indicates what بقى? That packet 1 and 2 and 3 and 4 did not arrive on time to the receiver. They might also be delayed, صح? But this delay is due to network congestion, probably. Otherwise these packets are getting lost in the network, and that's another serious problem, right? But in all cases, that's a more drastic situation, right? So in that case, I assume that there is a serious state of network congestion or network problem. You see the difference between the two, right? So in the first event, there are some packets getting through. So the one packet getting delayed is an intermittent event.
Does that mean that there's congestion?
Yeah, it's not, yes, does not really indicate that there is, but for all cases, I have to drop. For both cases, I have to drop. Why? Because even for these 3 duplicate acts, this segment seems to be delayed for a long time. Okay? So as long as there is an adverse event like this, I have to drop. Okay? And that's why when there are some variations in TCP implementation. Some algorithms, they treat both events similarly. Okay? And some implementations for TCP, they treat them differently. Both of them, they still comply with the TCP standards. Okay, so the TCP standard does not really dictate that you have to use a specific approach to differentiate between these two events. Okay, so we have so we talked about additive increase, multiplicative decrease. And we talked about slow start last time. So we said that slow start, during the slow start, it's called slow start, but it's actually misleading a little bit. Why? Because it's not really slow in the sense that we have to go slow. We start from a very low value for the congestion window, which is probably 1. But we increase very fast based on incrementing this congestion window with every single acknowledgement we receive. So we will see this visually, that we start from a very low number, but we actually move very fast. So that's how it works. So the TCP, we call it TCP Reno. So with the first acknowledgement, we increment the congestion window. When we increment the congestion window, this means that we can send now 2 segments. So we send the 2 segments. If we receive 2 acknowledgements, we increment twice. So the congestion window becomes 4. So which means that we can send now 4 segments. If everything goes well and we receive 4 acknowledgements, then this will become 8. So we start from a low number, but we actually move very fast. Okay? So when we begin the connection, we increase the rate exponentially. Okay? But we have to be careful, because when we move very fast and increase it very, very fast like this, chances are you will hit the capacity. You will hit the capacity. It's by design. Yes, it's by design. ما هو TCP, in terms of congestion control, it tries to reach to approach the limit of the shared channel. Because that's the objective. You are trying to utilize the channel efficiently, right?
And once we reach the capacity, what will happen?
Once you reach the capacity, one of the 2 events will happen. اللي هم ال 3 duplicate acts or the timeout. Okay? So now you have to drop. Now you have to drop. So when you begin, you start to grow the congestion window very fast, okay, until you get 1 event. When you get 1 event, there is one interesting thing that happens. We have to divide the transmission rate into 2 phases. One rate, we call it the slow start, and another phase we call it congestion avoidance. So we'll see how this works. So before that, we have, after 3 duplicate acts, the congestion window is always cut to half. The congestion window is always cut to half. Okay, that's what we call the Reno protocol. So we'll talk about the different congestion approaches. All of them, by the way, they comply with the TCP standards. Okay, but there are slight differences between each one. After the timeout, the congestion window goes down to 1, because we said that we have to differentiate between the 2 events. One is not as serious as the other. So if we get 3 duplicate event, we drop by half. If we get timeout, we drop back to 1. Okay, so someone might say we drop back to 1, معناها we start from scratch. As we said, we move forward very fast. We grow exponentially, right? And as we see for the next time بقى, we will have 2 phases. We will have 2 phases. One is called the slow start, but we have the other phase which is called congestion avoidance, and there is clear difference between the 2. So after the timeout event, the congestion window is dropped down to 1, and window then grows exponentially using the slow start mechanism. That figure, but that time figure is very, very important. Is very important. Okay. There are 2 slight variations in the implementation of TCP. One is called Tahoe, and the other one is called Reno, or sometimes they call this Reno and the other one New Reno, something like that. This, no need to stick to the names. In the assignment, actually, assignment 3 will have like 4 congestion mechanisms to analyze the performance for. But this figure is actually very important, and I can ask you potentially tons of questions about this figure. Tons of questions. This will enrich any incoming exam with lots of questions. So to understand this well, you need to keep in mind that the x-axis here represents the RTT, the full round trip. The full round trip, okay? So the y-axis represents the congestion window. So this is the congestion window, and this is the RTT time, okay? So we start from a congestion window of 1. This is 1, okay? After 1 RTT, the 1 becomes 2. After 1 RTT, the 2 becomes 4. And then 8. صح كده? Okay? Assuming that we don't have this, forget about this line. We go from 8 to 16, and so on, until an event happens. When an event happens, assuming that we go like this, and there is an event. Okay? When the first event happens, what we do is that we set a threshold here called slow start threshold. The slow start threshold. We set this.
This is when the event.
Yes, when the event happens. Okay? We set this slow start threshold to half the congestion window at this point. So this curve, this figure here, tells me that there was actually some transmission happening, and the last congestion window here was what? Bravo, Ali. Yes. So here it was 16, so the slow start threshold got set to 8. Okay? When we put the slow start threshold to 8, it divides the transmission into 2 phases. Okay? One phase, we call it the slow start. That's why it's called slow start threshold. Okay? Once we hit that threshold, we start to increment the congestion window by 1 for every RTT, not for every acknowledgement. Okay? Why? Why? Because the slow start threshold now indicates that you might be approaching the critical limit. Okay? So you need to be careful. That's why this phase now is called the congestion avoidance. Okay? Once we get another event here, this event happened now at congestion window 12. Is it supposed to be always 16? No. Why? The problem is that we don't have full visibility to the network, so we never know. The network load is dynamic. صح? So we never know. Sometimes we hit the capacity at 16, at 15, at 12. You never know. And the problem is that TCP does this congestion control end-to-end, end application to end application, but we don't have visibility. So we don't have exact estimate how much is the load on the network now. صح? So here it's 12. So we set the slow start threshold to 6. So the new slow start threshold will be set to 6. Okay? And now we have to say, what is this event? Is it a 3 duplicate act or a timeout? Okay? That's when there is a slight variation in the 2 possible implementations for the congestion control. TCP Reno, okay, if it's 3 duplicate acts, it goes to the congestion avoidance phase directly. Okay? But if it's a timeout, it drops to 1. ماشي? TCP Tahoe does not differentiate. So it blindly drops down to 1. So it goes into this sawtooth behavior all the time. Okay?
So in this diagram, we don't see the tahoe, yes? It's not a tahoe, yes?
It's not what?
It's not a tahoe, it's not a tahoe, this diagram, right?
This blue one is the TCP Tahoe. The black one is the TCP Reno.
So my second event
Right,
happened at 12.
right. So TCP Tahoe, the blue line, TCP Tahoe, regardless of the type of the event, regardless, it will drop down to 1. Okay? TCP Reno, it has like one if statement. If that event type is 3 duplicate acts, it goes to 6 directly. It goes to the collision avoidance phase directly. It doesn't go back to the slow start phase. That's the only difference between the two. Very, very slight difference, very subtle difference. Okay? So supposedly TCP Reno tries to be more aggressive but you will be able to analyze the behavior in more details as part of the assignment.
So why we call it slow start? Why we call it slow start?
It's a bit misleading. You're right. It's a bit misleading, even though it's called slow start, but it goes very fast. Slow start معناها it starts from a very low number. So it starts from 1, but it grows very fast. Okay? So that's the difference between them. So if I were to ask you, مثلا, how many segments are sent here at this stage?
This is an RTT.
How many segments?
Can we have the number of segments?
That's what I'm asking.
Yes, it's 11.
Huh?
Count.
We can't know because this is an RTT.
11? Let's see. Here it's 1, plus 2, plus 4, plus 8.
I have to see.
طبعا. So it's a geometric series actually. Right?
So the question is how many?
Yes.
We send or
Yes. And then after 8, we go to 9,
But this
and then 10, and then 11.
The threshold will make a difference here.
Right?
The threshold makes a difference.
طبعا.
Individual.
طبعا.
so if the question was how many we can send, it will be
لا, not how many we can send. How many segments have been sent until this point?
summation.
It's the summation of all. Okay. تمام كده? Any questions? Did we miss anything? I think we are done here. Okay. So
number of segments from this diagram, if I want to translate it to number of segments, we don't have any segments. Can I do this?
I don't get the question, sorry.
يعني this diagram gives me some information.
Uh-huh.
Can I regenerate the same diagram, but instead of having the x-axis as a transmission round, I'll have it as number of packets?
Not number of packets, but it would be the acknowledgements, the number of acknowledgements you receive. Yes.
Okay.
The number of acknowledgements you receive. Another very تفضل.
The diagram shows the RTT, right? But what's the difference? Like, can I regenerate the same, but
Another very important question. Okay, we discussed the congestion control for TCP. If I were to have two end applications like this, okay, sending transmission segments to any destination, doesn't matter, but through a shared network, okay? The question is, will this congestion approach guarantee fairness between these two connections or not? With this behavior, اللي هو البيهيفير الغريب اللي احنا it does.
It will not.
Seemingly, you would assume it doesn't, صح? But it does. That's the beauty of it.
Because we don't guarantee that everyone will follow it.
صح. But regardless, you will see with this simple approach that we have is that every time we hit an event, we divide the congestion window by 2. As simple as that, we guarantee fairness.
Even
Okay.
if I'm aggressively.
Yes, even if you are, yes. Let's see how. How do we do this? So how do we do this? So this is actually one of the things that any congestion technique tries to achieve. Because if we don't have fairness, there is something wrong. So this way, some applications, they will eat the bandwidth of the network, and the other applications will starve. صح? That situation is also not good. Okay? طيب. So how do we guarantee or how do we show that TCP indeed achieves fairness? So if we were to assume بس يعني very simple scenario, very simple scenario, that we have 2 connections, okay? The rate for each connection is on one axis. So this means that this line has an equation which is assuming that مثلا one connection has R1 and the other connection has R2. Okay? So this is R1 and this is R2. And we have the total capacity of the network. طبعا it varies in reality, but let's assume that it's R. Let's assume that it's R on average. Okay? طيب. So what is the equation of this line?
X equals 1. X equals 1. R1 equals R2.
R1 equals R2. برافو عليك. تمام. So this equation is represented as R1 equals R2. طيب. This equation, the equation of this line is represented by R1 plus R2 equals R. صح? صح? So you would assume that R1 plus R2 at any point of time should not exceed R. Otherwise, if it exceeds R, we'll start to hit many events of packet drop. صح كده? Okay. So as you said, assuming that we started here from any point. We start from any point. And as you said, we might start from different points. And that makes sense because the connections start at different time. So here, I have this is R1 at this point, and this is R2. Okay? So the capital R1 equals small r1, and capital R2 equals small r2. Okay? So this point is not, it does not achieve R1. But here, the small r1 plus small r2 are less than R, less than capital R. So that's why we are below that line, and everything is fine, and we're not supposed to have a drop event at this point. صح? So in that case, both connections, they will start to increase the congestion window, okay, right? Until they go beyond R. When they go beyond R, and due to the queuing, okay, we'll start to hit some event of packet drop, whether it's 3 duplicate acts or timeout, whatever. So both of them at that point are supposed to do what? Decrease by by half. لا, by half. By half. صح? That's the key here بقى. That's the key here بقى. Yeah, did you get the trick here? That's the key. Both of them, they will drop by half. But the half for the one that has larger R will be more than the half of this smaller R. Okay?
Which is a step down.
Yes. So we'll get down to here. Okay? So when we get down to here, assuming that both of them, they will get triggered by the loss event, right? So they will both drop, even if they drop at a slightly different time. But they will get to a point around here, right? So they will start to grow again. And then if an event happens when they go beyond R, they will also drop. So they will keep A. You see the zigzag. It approaches this beautiful point. This beautiful point is where R1 plus R2 equals R. So you will always get around this and hover. Okay? And that achieves R1 plus R2 equals R, and actually R1 equals R2 equals R divided by 2. صح كده؟ واضحة كده؟ So the trick is that when you drop to half, your half is different from my half. So if you have a bigger R, you will drop drastically. If you have a smaller R, you will drop less. Yes. Yes. This is the trick that makes it fair.
Here it looks like this because the two R's are equal, right? But if we change the R and one is bigger than the others.
Oh, here one is bigger than the other. They start from a different point.
Okay.
Yeah, you see here R2 is much larger than R1, right? But the idea is that when they drop, R2 will drop drastically, and R1 will drop. The drop is proportional to the value, to the original value, right? So that's why you will keep zigzagging close to this point, which is R1 equals R2 equals big R divided by 2. And that's what you need, okay? So that's good, that's what we want. So TCP here achieves fairness, which is good, but there is a small drawback here. There's a small drawback. It achieves this by every single TCP connection. So assuming that you have 10 TCP connections, okay, and the capacity is R, so each of these connections will get R divided by 10. صح? Divided by 10. So TCP achieves fairness by connection. That's very important. I will show you now why am I stressing on this. So, does UDP guarantee fairness? It doesn't. Of course, UDP does not do anything. It does not do reliable transmission. It does not do congestion control. It does not do flow control. It doesn't do anything. The only thing that it does is just multiplexing, demultiplexing. That's it. Yes, multiplexing, demultiplexing. But it's actually very attractive for applications such as multimedia and video. So does that mean that these types of applications do not require flow control or congestion control? They do, صح? So this tells you that if UDP doesn't do this, someone else has to. Right? So UDP will achieve the multiplexing and demultiplexing, okay? But it cannot be used on its own without another protocol on top of it. So UDP is always, in many cases, it's used in addition to other protocols. For video and audio, very commonly there is a protocol called RTP or RTSP, real-time protocol or real-time session protocol. Okay?
And those two relies on which layer?
Application layer.
Yeah.
Application layer. So TCP will perform multiplexing and demultiplexing at the transport layer, and RTP and RTSP, they will run at the application layer performing flow control and congestion. Okay? So there has to be flow control, otherwise we will cause problems to the receiver or to the network. You don't want this to happen. But the good thing is that for TCP, we achieve the fairness, and we achieve congestion control, and we achieve flow control. However, there is a very interesting phenomenon. There's nothing that prevents any application, we're talking about one end application, to open tens of TCP connections. Okay? So one application will open 10 TCP connections. So in that case, this application will in fact eat the bandwidth. Nothing would stop it from doing that. And that actually, that approach is very commonly used by peer-to-peer networks. اللي هي Emule وجناتيلا. I'm not sure if you've heard about these networks. Some peer-to-peer networks, they utilize this approach. So your peer software can open 10 TCP connections to download the same file from a remote destination. So if you open 10 connections of TCP, this means that your throughput, your effective rate is multiplied by 10. Okay? So assuming that you have a scenario like this, you have n different sources, n different applications. Okay? Each application has one TCP connection. Okay? And they are all sharing a shared network that has a capacity of R. Okay? So supposedly, the effective rate for each one is R over N, صح؟ تمام كده؟ So each application will see R over N rate on average. Okay? طيب. Very smart application بقى. It will try to open another N TCP connections. Okay? So one application has small n, okay, different TCP connections. What would be the rate that this application will see?
N R over N plus N.
So, bravo عليك. So it will be n times R divided by big N plus small n. Okay? واضحة دي جت منين؟ So this and the others they will have a R divided by capital N. So this one got an advantage by just establishing more TCP connections. And that's actually one of the advantages that some software they try to abuse. يعني. They try to create many TCP connections, concurrent TCP connections, to download the same file. So by increasing the number of TCP connections, you can effectively increase the throughput and download the file faster. And you eat the bandwidth of the network. Okay? So that's a drawback in TCP. تفضل.
This affects the fairness, yeah.
Yes, but TCP will achieve fairness per connection. That's the key. It will achieve fairness per connection. So it will deal with these connections as independent connections regardless of which application it's coming from.
So at the end, this is
It's a fair protocol, بس هي المشكلة الوحيدة إن هو per connection.
It's a negative point to TCP fairness.
Well, I wouldn't say it's a negative point to TCP. It's a negative point in general that needs to be handled either by TCP or by another protocol, but it needs to be managed somehow. Okay? But that's how TCP works. It's per connection. Okay? So there has to be some kind of network management protocol that says, okay, so these connections are coming from the same application, so I have to do some resource allocation based on where they are coming from. That's a problem that I'm not aware of any internet protocol that performs this. We'll study this in network protocol, in network layer. Okay? We understand this phenomenon now. So this is the slight problem. So this is the end of this chapter. So in this chapter, we talked about many things. We talked about multiplexing and demultiplexing as the minimum functionality for any transport layer protocol. And we achieve this through the source port and destination port, as we have discussed. In addition to that, some protocols like TCP, they provide reliable data transfer, and we talked about many variations of reliable data transfer, and we talked about go back N and selective repeat, and how TCP achieves a reliable data transfer, which is a mix of both. Okay? We talked about flow control, where we try to avoid overwhelming the receiver by controlling the transmission window or the congestion window, okay, to be lower than the receiver window, which we receive it as part of the acknowledgement from the receiver. And then we talked about congestion control with the different variations based on the slow start mechanism and the congestion avoidance mechanism. ماشي كده؟ And finally, we talked about the fairness phenomenon. One very big message that we want to talk about here, before we break, يعني, now we are leaving the edge. So before we leave the edge network, okay, and we start to dive into the network, the core network, we start to have a deep dive into the core network to see the routers and how they work and so on and so forth. We need to understand a very clear message here, that the TCP/IP stack tries to push the complexity towards the edge. It's a philosophy. Why do we need to do this? Yani, what I mean is, we try to push the functionality as much as we can towards the edge. Because you would think that, why don't we address flow control and congestion control in the network layer? Is it possible? Yes, it's possible.
But it required to transmit the data first, and always communication is
No,
not
you're
possible.
trying to avoid processing. You do the processing at the edge.
Right.
Yeah, that's what we're trying to do.
Yeah.
صح, we do the flow control and congestion control at the edge. Why? Because we do this end to end. One application can have how many connections? 10, 100, right? So one application can maintain مثلا how many TCP and UDP connections altogether? 100, 200? If you open all the windows مثلا on your host مثلا, okay? Each one has a transport layer connection. How many would you think you would have at any point of time? 10, 20, 100? Big deal. Okay? Let's look at the network. If we want to do flow control and congestion control for every single connection end to end,
Millions.
can you imagine how many connections we need to handle? Okay? Can you imagine? So that's why we select to push flow control and congestion control towards the edge. It's done end to end. And we paid the cost for this. What was the cost? We do the congestion control with no visibility to the network. صح? And we had to make certain assumptions, but we have no other choice. That's the only way we can do it with high level of scalability. If we do this at the edge, we maintain like 10, 20, 100 connections. That's possible. But if we do this at the network, and we will see, we'll appreciate this now. Right after the break, we'll talk about the circuit, the network circuit, and we will see if we were to handle this per connection at the network level, one router would potentially have to deal with يعني now like tens of billions of connections. Tens of billions of connections. Okay? So we cannot achieve scalability. That's the main reason why all network layer protocols have lost ground to IP. Okay? Why? Because IP is built on this philosophy that complexity is pushed towards the edge so that the network would be simple. And IP is very simple. IP is built on what? Best effort. I don't have any guarantees. صح? We can do that at IP, assuming that the edge will take care of flow control and congestion control. So we don't provide reliable transfer in IP. Why? Because it will be taken care of by TCP. We don't provide congestion control or flow control at the network layer. We don't do this. Why? Because it's taken care of by the edge or by TCP in an end-to-end way. واضحة دي? So it's a big philosophy, and it actually, this is what makes internet really scalable. And they started, عشان بس just to appreciate this, when the internet was very small, they started with the perception, yes, we can provide per connection behavior. So we'll go now through the network circuits, and we will see how many connections the router can potentially deal with. It's not possible. It's not scalable. And now with the potential billions of devices, can you imagine how many of these the router has to deal with? It's huge number. You cannot do this. Okay? So that's why IP is kept very, very simple, with the assumption that other protocols will take care of other things. ماشي? So let's break and come back. We'll start chapter 4. Chapter 4 talks about network layer. The goals for this chapter is to understand the principles behind the network layer services. As we all know, network layer facilitates the communication between what and what? We said transport layer facilitates the communication end-to-end between two end applications or two processes, end-to-end, صح? The network layer facilitates communication between here and
لا between devices, not routers.
في disagreement.
Between routers,
Devices?
between routers.
Routers ولا devices؟
Routers uses MAC address. Routers uses MAC address. لا switches MAC address.
هتزعلني منك.
نمشي حبة بنتحكم فوق.
Yeah, okay. Between IPs, yes. IP represent what? The IP represents what?
Network layer.
A host, not a device. Okay? So network layer facilitates the communication between hosts or two networks. يعني هم two answers are correct actually. So between host and a host, or between network and a network. And by network here I mean a router. Okay? Or between host and a network. Or between network and a host. But definitely.
What's the difference between host and device?
Yeah, device is physical device. So refers to physical device, which is very commonly represented by physical address, which is MAC address. Yes. And by device here, I may actually mean a host, router is a device, صح? Switch is a device, hub is a device, صح? It's not a device. Device is not an accurate word. Host. A host is represented by an IP, which is a logical address. It's not a physical address. صح? When you move from one location to another, IP changes. Does that mean that your device changes? No. But it takes a logical address for every location you move to. صح? So IP is a logical way of addressing. It's not a physical address. Okay? And the network layer facilitates the communication between host and a host, or network and a network. Okay? طيب. There is a difference in the router between what we call routing. طبعا the main idea for we said flow control and congestion control end to end. خلاص, we don't have to worry about that. So in the network, we care about routing. So what is the difference between routing and forwarding? Okay? So we'll answer this. What is the implementation in the internet in terms of the router? So we'll take a deep dive inside the router, and we'll look at the router architecture in terms of hardware. What is the hardware inside the router? What is the software? What is the interaction between the two? How does the router perform packet forwarding from inside? In addition, of course, to how the routing process is done and how packet forwarding is done. So these are the topics that we will cover in this chapter. This is even a longer chapter compared to the transport layer. So so we'll talk about, in the introduction, we'll talk about in general what is the network layer service, and then we'll talk about the difference between virtual circuit and datagram. We talked about similar thing في البداية when we talked about the difference between packet switching and circuit switching. When we say switching, we refer to data link layer, physical circuits. But here, it's a virtual circuit. In the network layer, we have, and actually in the transport layer, we have also a connection-oriented and connectionless. Okay? That also, facilitates the establishment of a logical connection end-to-end. Logical connection end-to-end can be divided into multiple virtual circuits in the network layer, which can be further subdivided into multiple physical circuits using data link layer. فهمنا الفرق عشان just to have a complete understanding of the big picture. So for each layer, we try to have some kind of logical circuit establishment or a connection establishment, and that, as we said before, helps us to maintain the order of transmission and facilitates some reliable transmission, and also gives us some idea to provision some resources for this virtual circuit or for the connection end-to-end. Okay? So we'll talk about the difference between the virtual circuit and datagram. Before this, we need to talk about the difference between forwarding and routing. Routing is the process of planning how the packet, and here, of course, we'll talk about packets, not segments بقى خلاص. وتركنا segments. Here we're talking about packets. So if I want to launch like a caravan of cars to go from QU to Dukhan, right? So we can do a routing. Routing is the process of planning how these cars should go from QU all the way to Dukhan. Okay? So we plan the route end to end. Okay? Forwarding talks about the fact that for every intersection, okay, what do we do locally in order to follow that route end to end? Okay? So in the network layer, we need to do routing, okay, which is we plan that all the packets that are coming to a particular destination network or particular destination host should follow certain route end to end. Okay? And then for each router each router has to take a local decision to abide by this end-to-end route. This is a slight difference between the two. So routing is the process of planning the trip end-to-end. But forwarding process of getting through the single intersection. So imagine like a router is like a person who is standing in every roundabout. Okay? A person standing in every roundabout. You get to this roundabout and then you ask that person, I need to go to Dukhan. What do I do? He say, okay, so go left, go right, go straight. Okay? So that's what the router does. It takes some local decision, which is what we refer to as packet forwarding, that hopefully will lead to a specific deterministic route end-to-end. Why am I saying hopefully? Because IP does not guarantee that you will follow the same route end-to-end. IP never promised. Okay? So there might be some inconsistency in the routing table of the routers, in which case the packet will actually circulate in the network, will go through packet loops. Okay? Might be completely lost. Not because of traffic jam, because it's lost, it gets lost. The driver of the car is like he got مفيش crazy. هتقول له go to Dukhan through this route, and he insists to go through another route, so he got lost completely. Does that happen in the network? Yes, it does. Some routers might perform incorrect packet forwarding, which might lead to packet loss. One of the reasons is network attacks. So I can perform network intrusion and cause the routers to take incorrect routing decisions or forwarding decisions. Okay? Routing is to determine the route taken by the packets from source to destination. And that's usually done by routing algorithms or routing protocols. Like بقى REP, you studied REP, some of you يعني studied REP, or EIGRP, or OSPF. Okay? These are routing protocols which are being used by IP. Okay? So all these all these routing algorithms can be divided into two categories, which we will discuss in this chapter. You have a question?
Victor, when you are saying IP protocol, we're
Mhm.
talking about which layer?
Network layer.
Network.
IP network layer. IP network layer, man. There's no other option. IP is network layer.
دكتور شو السنتنس اللي تربط ال TCP نقول TCP UDP بعدين نقول
IP TCP IP. يعني when I say TCP لا, when I say TCP IP I mean the TCP IP stack, which means TCP in the transport layer and IP in the network layer.
Okay, yeah.
They refer to that as the TCP IP protocol model. So this is the most common protocol model in the internet, okay, which refers to TCP in the transport layer and IP in the network layer. Okay, the data link layer or the network access layer can use Ethernet or can use wireless or whatever. ماشي كده؟ طيب. So that's the routing algorithms or routing protocols, they are being used to fill that table, which we refer to as routing table. However, it's actually being used for local packet forwarding. Okay? So the routing protocols, they plan the pass, the pass end to end between all the hosts in the internet to all the hosts, or all the networks to all the networks. Okay? Based on running this planning process, they allow these routers to fill their routing table. These routing tables are later on being used by the routers to perform what we call a local packet forwarding. So if I have a packet coming to this router, all I need to look at is the destination IP or the destination identifier. In case of IP, it's destination IP. Okay? That's all I need to look at. I don't need to look at anything else. And I don't need to look at where the packet is coming from, because the source address is also there. صح? I don't look at it. For me, it's insignificant. Okay? And I will tell you why. If we consider the source IP, then we're getting to another level. ماشي? So all I need to look at is the destination IP. So I look at it in the routing table. Hopefully I will find it. And I will tell you, what if I don't find it? I will talk about this, okay? So this is like exactly equivalent to the fact that I came to this roundabout and I'm asking the person, I need to go to Dukhan. So Dukhan is actually on this exit 2. So go to exit 2. When I go to exit 2, I will typically go to this router, which there is another person there that I will ask him. And hopefully, يعني, by following this repeated questions, I will reach to the final destination. Is there a guarantee? No. Is there a possibility to get lost? Yes. ماشي? So this is the difference between routing and forwarding or local packet forwarding. So now there is the topic of virtual circuit versus datagram networks. So virtual circuit here refers to the fact that the communication between the different host-to-host or network-to-network will be divided in the network level as virtual circuits that identifies where the packets are coming from and where they are going to. Okay? Versus datagram does not distinguish أصلاً where the packet is coming from. For me, I divide all the packets going to a certain destination or certain network بحالها, okay, to go through one path. Well, that's it. So we need to study the two concepts and see which one is more scalable, which one is more feasible on the internet. So this is analogous in a way with when we talk about حتى transport layer protocol, we said that it's connection oriented versus connectionless. That's slightly different because in transport layer we're talking about end application to end application. It's one end connection. Okay. Here we're talking about logical circuits end to end between individual hosts. Okay, at the router level. So the datagram network provides network layer connectionless service, which means I don't have to establish a virtual circuit before I send the packets. So these are the two possibilities. So if I were to have host and a host, and here the network, and the network has a router. Okay? So this is the, sorry, let's make it source and destination. If I have the source, if I have the source here, having multiple connections, all of them are going to that destination. How does the router manage this? Or if I have another source here and another source here, so this is source 1, this is source 2, this is source 3, all of them are sending to the same destination. Let's talk about this scenario. Okay? So the router now is looking at all these incoming traffic from multiple sources. Okay? So if they are all going to the same destination, how would I manage this if I were to talk about virtual circuit using datagram? For virtual circuit, I will potentially deal with each of these connections as a different virtual circuit. Each of these connections will be dealt with as a separate and unique virtual circuit. Even if they are going to the same destination, yes. And in fact, the router will give a different virtual circuit number to each of these connections. And in order for the router to do this, it has to first establish that virtual connection end-to-end before it facilitates the transmission. Similar to connection-oriented design. Okay? طيب, what is bad? What's good and what's bad about this?
It's good that it guarantees the path before transmitting the data.
برافو عليك. Yes, that's one. صح.
Well, the second thing that it needs to buffer or store everything.
برافو عليك. Yes. That's perfect answer. So I can simply, okay, I can simply establish and guarantee the route for all the packets coming from this source to that destination to go through the same route because it's already established. And I can even go further than this and book or reserve a certain buffer size in the router for this particular connection. صح? Okay? طيب. Which means that I can have on average يعني the same average queuing delay, which can in a way guarantee the end-to-end delay and the throughput, of course. تمام? Which means I can provide predictable behavior. or deterministic behavior at the virtual circuit level. Okay? That's good. صح? This is good. Okay? What's bad about it?
It's not logical to do it. Because
أيوة.
on a small network, yeah, that's manageable, but larger networks, it will increase exponentially. You can't have an exponentially buffer.
Yes, bravo عليك. Yeah. So the router will have to potentially now manage potentially millions of these virtual circuits. And to appreciate this, let's talk about the other alternative. If we were to talk about datagram, I don't have to establish a connection. So what I told you is that anything that goes to a destination, okay, will go through one behavior, which means that potentially here, the router needs to maintain one router table entry for that destination, that represents all these logical connections. Okay? So in that case, the router had to deal with only one entry or one handling for all these connections. I don't have to establish a virtual circuit. I don't have to go through the connection establishment phase. I don't have to do this. Okay? طيب. So if I were to manage the virtual circuits, the router potentially has to manage millions of these virtual circuits, even if they are going through the same destination. But the router has to deal with millions of these connections. Okay? Type, this is not scalable, especially that potentially nowadays in the internet we're talking about potentially millions and in some cases billions of these devices or these connections. So imagine one router had to deal with billions of these. So in the past, virtual circuit network protocols, they were in a way possible in low topology network or small topology network. Like if the network is composed of like 10 routers, 4 or 5 routers, things like that, that's manageable. Because potentially the number of connections we have to deal with is not that huge. But can you imagine a router in the core network that has to deal with millions of these connections? It's not scalable. Okay? So the overhead here is huge. But the good thing about the virtual circuit is that we can provide per circuit deterministic behavior, which we missed if we were to talk about datagram. Talking about datagram, we miss this advantage. That's why in TCP it was very important to talk about fairness. It was very important to talk about flow control, congestion control, things like that. So we push these things, we push the per connection behavior to the edge. واضح كده؟ إنما في النتورك لا, we cannot do this. We're not in a situation to perform this. Okay? تمام. So so datagram network provides network layer connectionless service. We don't have to establish a virtual circuit, which means that we can forward the packet.
How does my routing table looks like when I'm talking about the diagram?
That's a good question. So we're talking about connectionless. How does the routing table get filled أصلا? Okay, there is routing algorithm or routing protocol that takes care of this. So in virtual circuit, I need to do initial signaling to establish the circuit before I transmit anything. Okay, and there is synchronization between first I have to establish the circuit, then I have to transmit. Okay, for datagram, the two phases are separated from each other. I can perform routing اللي هو planning I can perform that offline. So when the network first starts, that's why when the network first starts, I cannot just ask the host, okay, start to transmit. صح? Because the routing tables are empty. Transmit what? You will not have the person standing in the roundabout to ask him. Okay? So you need دايما when they start the network for the first time, they have to allow the network for it's called مش عارف it's called inception start or something like slow start كده.
Throw everyone in the
Yes, to allow the routers to exchange some signaling to prepare the routing tables. And that usually takes tens of seconds or potentially a few minutes حتى. Okay? During this time, you're not supposed to transmit anything. If you transmit anything, you will very frequently run into network loops. Because routing tables are not consistent. Okay? So you have to wait for this phase, which is done offline. Huh? It has nothing to do with circuits or virtual circuits. They are done offline, separately, asynchronously. Okay? And every time the network topology changes, that process runs in the back scene to update the routing table. But the transmission is moving on. It doesn't have to wait for anything. It doesn't have to establish a circuit. واضح الفرق ولا مش واضح؟ واضح؟
It's as if the router is the final destination, only at the beginning of the communication.
A router it might be the destination, or a host might be the destination. Doesn't matter. So when the routers start, they start to exchange some signaling messages, which allows the router to identify each other, and then they say, okay, so if I have a network in this area, I need to forward to this router because this router seems to have a direct connection to this network. Okay, so that's what we refer to as the routing algorithm or the routing protocol, like RIP, OSPF, or EIGRP. All these protocols, they take care of this, but that's done asynchronously in that case. It's a separate phase. Okay. Type. So virtual circuits, the source to destination path behaves much like a telephone circuit, but in telephone circuit, we discussed that before in data link. In telephone circuits, we usually talk about physical circuit, but not a virtual circuit. Physical circuit, which means that a physical connection between a switch and a switch in the data link layer. ماشي? So here we talk also about a call setup and tear down for each call before data can flow. So I have to establish that connection first, and it has to be synchronous to the transmission. Each packet carries a virtual circuit identifier. See, here we're not talking about IP. Why do I have to assign a virtual circuit? Because between the same source and the same destination, I might have multiple virtual circuits. صح? And I need to identify each of these. So you can think of this virtual circuit identifier similar to the datagram, which is identified by 4 variables, if you remember: port address, port source address, port destination address, IP, and so on. So I have to assign here a virtual circuit number for each connection end to end. Okay? Every router on the source destination path maintains a state command. This state is very important. In datagram, I don't have to do that. But here, why do I have to maintain the virtual circuits? Is to provide a special behavior for each of these circuits. So here, the state contains what? Contains how much buffer size do I have reserved for this virtual circuit? Okay? How much output bandwidth or rate can I assign to this virtual circuit? Okay? So each virtual circuit is associated with a state which maintains how much resources I can reserve for this virtual circuit. That's good. This is a good advantage. However, as we said, it's not scalable. مفهوم كده؟ the router state refers to بقى ايه the router resources in terms of bandwidth, buffer size and so on. Okay? This can provide اللي احنا قلنا عليه اللي هو predictable service or predictable behavior. So if I establish this virtual circuit, I can, for a good level of confidence, say that okay, so the throughput here will be like this. Will be X. Okay? I can have this confidence. But in datagram, as we all encounter, as we all can experience, it varies, goes up and down. I cannot guarantee anything. Okay? So a virtual circuit consists of path from a source to destination. The source can be a host or a network. Destination can be a host or a network. Okay, and we'll see the slight difference. Virtual circuit numbers, one number for each link along the path. So this virtual circuit number refers to the connection end-to-end. Entries in the forwarding table in the router along the path. So the router بقى will maintain a virtual circuit, and each virtual circuit will be mapped to an output interface and will be assigned bandwidth and buffer size and so on and so forth. Packet belonging to the virtual circuit carries this virtual circuit number. So the packets, the incoming packets would not have the IP in that case. They should have virtual circuit number. And the virtual circuit number here identifies the end-to-end path. Okay? Virtual circuit number can be changed on each link. This conflicts with what we discussed so far. If we're saying that virtual circuit refers to one deterministic route end-to-end, how come we say here that the virtual circuit number changed at every router? How come it changes, but it identifies the end-to-end virtual circuit? If it identifies the end-to-end virtual circuit, it's supposed to be one identifier, صح?
Maybe same IP addresses, but different phone numbers.
Here we're not talking about IP addresses. We're talking about virtual circuit number. But the virtual circuit number is supposed to refer to the end-to-end virtual circuit. But the virtual circuit number changes at every router.
So I'm rewriting the same thing.
Hmm?
I'm rewriting.
Yeah, but why does the virtual circuit number have to change at every router? This is what we need to.
وصلت الراوتر الثاني شلون تتكلم عن شيء كان بالراوتر الأول؟
Okay. You're thinking correctly. Yes, you're thinking correctly.
Yeah, because like he started with for example, he started at different point of time as the other.
And I'm just posing a question that we will answer in the following slide. But it's good that I'm getting all these answers.
So
it's very good.
The first router started as virtual numbers before the other router, so it's fine, so that they don't have the same.
That's in a way that's correct. Yeah, we'll talk about it in the figure just to make it clear. New virtual circuit number comes from the forwarding table. So the forwarding table, okay, will have the new virtual circuit number for every router. Okay, but that doesn't mean that the end-to-end is a different virtual circuit. It is the same. ماشي? That's how it looks like. So here, the incoming interface, there is an incoming interface. One, if the packet contains that virtual circuit number, that tells the router that I need to exit this packet to port number 3 and the outgoing virtual circuit interface. This is what we're talking about. It's supposed to be the same end-to-end virtual circuit, but here the virtual circuit number is 12, and when it gets output to port 3, the virtual circuit number changes to 22. Okay? Why cannot be 12? Again, I will answer. Don't worry. Supposedly and logically, it should be also 12, right? The only reason for this is that in order to maintain one virtual circuit number, you have to have all these routers agree on a global unique virtual circuit number for every connection end-to-end.
Which means you have to wait for a large amount of time before it was.
برافو عليك. Yes. So these virtual circuit numbers have to be globally unique.
Yeah,
Yeah?
why do you take this up?
Yeah, why do we have to go through this overhead? So we can assign local virtual circuit numbers to the same virtual circuit end to end, but the number doesn't have to be unique. However, the virtual circuit end to end is the same, but the number doesn't have to be unique. So this simple approach allows us to not to wait for the routers to agree on a globally unique virtual number. That's the only reason, يعني. Okay? But you see برضو هنا some interesting thing. So here, from the same source, from the incoming interface, we have here 1 and we have here 1, but you have here different virtual circuit number, and the output might go to the same or different with different virtual circuit number. And what that means is that potentially you have many incoming virtual circuits from the same port, and they are going to the same port, but they are different virtual circuit number. That's the main difference between the virtual circuit and the datagram. In datagram will deal with this as only one entry in the routing table. But here I can potentially have tens or maybe hundreds or millions of these virtual circuits, which we have to maintain and handle separately, which is a big overhead for the router. The router now has to deal with millions of these virtual circuits. And not only that, remember here command there is a state, which is missing from this table. The state here has to be maintained for every single virtual circuit. And this one will be different from this one. So the amount of buffer size I reserve, the amount of bandwidth, and so on, will be different from one to another. Okay? That's a huge overhead. This is a huge overhead for the router. واضح كده؟ So this is the virtual circuit, and we don't have here بقى IP address, we have virtual circuit number.
Can we say that the first one is one application and the other one is another application?
لا ما تقولش يعني ممكن يعني it could be one application صح؟
Okay.
Could be one application or one connection ماشي؟ Or one traffic flow or one process. All of these are possible. ماشي؟ The virtual circuit signaling, this is what we use for call setup and tear down. So we have to establish a virtual circuit first. So the way that we come up with these virtual circuit numbers is through first, we have to send a signal. Signal يعني a small message. This is like control message. It's not a data message. It doesn't contain any data. And it has to go to the first router. So the first router will say, okay, so there is a new call. It's like you dial the number of someone. He has to accept. While your request goes all the way to the person and then comes back on this, moving back and forth, all the routers along the way, they reserve this virtual circuit, okay? Which contains the virtual circuit number, the state, including the buffer size, the bandwidth, everything will be established and booked beforehand, okay? So that's the process of. So it goes through initiate call, which will go to the first router. So the first router will say, okay, so I need to reserve something. So let me see if I have some buffer size. This router might send back a rejection, by the way, saying I don't have any buffer size. And that's one disadvantage for virtual circuit.
What happened?
You can establish a call, okay? Once you establish certain number of calls, then the router might say, so I ran out of bandwidth, I ran out of buffer. Some of these virtual circuits, by the way, you are calling someone, okay, so I called someone, I use my phone, I call someone, and then after he answers, I put the phone down and leave. Which means technically I'm not using that. I'm not using the connection, but it's reserved. So you're not utilizing all this bandwidth, but it's reserved for you in advance. So someone else might start a call. It doesn't happen nowadays because nowadays we're using all datagram networks, okay? But in the past, we live these days, we are old people, we live these days. We call and we hear the very nice message that we all hate. All circuits are busy now. Please call again later. We used to hear this a lot. So you try to call someone مثلا in US ولا حاجة, all circuits are busy now. Please call again later. Why? Because all the switches are consumed. Even if someone on the other side of the world is actually not speaking, not doing anything, but he's reserving the resources from the network, unfortunately. So that's how it works. Datagram doesn't do this. That's why we said that for circuit switching or virtual circuits, we used to charge people by the second, by the time, regardless of whether you're talking or not. But when we download a file, we get charged by the byte. So if you're not downloading anything, you're not getting any charges. Okay? So this initiation call will go through the routers. The routers will see whether they have initial buffer size or not. If not, they will send a rejection. If yes, they will have it committed, but not booked. They will have it committed but not booked. Okay? Then it goes through the other routers. If they all agree, خلاص, they have the buffer size and everything, it goes all the way to the other network, and the network says, oh, okay, خلاص, accept. Once we accept, it goes back to all the routers, and then the routers will say, okay, so I will reserve. Only then they will reserve. Okay? Once they reserve, معناها the virtual circuit has been established. And then only then we start to send data flow. واضح هنا؟ Datagram doesn't do this. No connection established. Nothing. Packets going from the same source to the same destination, there are some scenarios where these packets, the same packets going to the same destination, but they take different routes. There's no guarantee. Okay? They might take different routes, they might get lost. But you will never be able to consume network resources without using them. This is the biggest advantage. The other thing is that the network is highly scalable because the network layer protocol is very simple. So I can maintain potentially huge amount of traffic on the network, and the routing table, as we will see in a minute, the routing table is very small. It doesn't have to be very big.
So it guarantees much more utilization than
It guarantees utilization, and also the router doesn't have to maintain a huge routing table of billions of bytes. لا, it's very small. Because it doesn't need to distinguish where the packet is coming from. I don't care about this. Okay? So datagram forwarding, let's stop here maybe عشان نديلها فرصة ولا ايه؟ خلاص let's stop here. خلاص خلينا نستوب هنا.